Hello everyone, this is me Kunal Murke and today I am here with a new topic which is automata theory and compiler design in which we are going to learn about non-finite automata. So now let us get on to the introduction to the finite automata. Finite automata are theoretical models of computation which are used in computer science and mathematics. They consist of states, transition between the states and acceptance states. Whereas non-deterministic finite automata are the type of finite automata where the transitions from one state to another are not uniquely determined by the input symbol which is being read. So what is non-deterministic finite automata? A non-deterministic finite automata is a computational model that can be in one of the several states at any given time and can transition to one or more states based on the input symbols which is being read. Unlike deterministic finite automatas, NFAs have multiple transitions from a single state for the same input symbol. So now let us know the components of NFA. NFAs consists of states, alphabets, transition functions, start state, and accept state. In the states, they represent different configurations of the automata. Alphabets are the one which are set of input symbols. Transition functions specify the next states given the current state and the input symbol. Start state is the one which is the initial state of the automata and accept states in which the automata accepts the input strings. So what are the transition functions in NFA? Let us take an illustrative example of NFA that can provide a clearer example of its operational behavior. Visual representation of NFA with states, transitions, and input symbols aids in the comprehension. A diagram depicting the NFA structure along with the transition table showcasing the transition functions offer a comprehensive view. Through an example, we can observe how non-deterministic allows multiple possible transitions, contributing to the expressive power of NFAs. So, with the help of examples, we can understand these transition functions of NFA in a easier and better manner. So, let us understand the NFA with the help of small example. Consider the following example of an NFA, where we have states, alphabets, transition functions, start state, and accepted states. Let us take three states initially, which are represented by Q0, Q1, and Q2, and the alphabets are 0 and 1. The transition functions delta of Q0, 0 is equal to Q0, Q1, and the transition function of Q1, which is the second state, is delta of Q1, 1 is equal to Q2, and the last transition function of Q2 is delta of Q2, epsilon naught is equal to Q0, in which we have Q0 as the start state and the accepted states are Q0 and Q2. The start state is represented by a single circle and the accepted states or final states are represented by double circle. So now we'll discuss about acceptance in NFA. Acceptance in NFA is determined by existing of at least one path from the start state to an accept state that matches the input string. This contrasts with DFA where only one path is permissible. NFA acceptance conditions may include reaching an accepted state or having an empty stack. This is flexible acceptance criteria which enhances the expressive power of NFA, enabling them to recognize a broader language compared to DFS. So let us discuss and differentiate about NFA versus DFA, where NFA stands for non-deterministic finite automata and DFA is for deterministic finite automata. These both NFA and DFA differ primarily in their transition mechanisms. While DFAs have precisely one transition per state and the input symbol, NFAs allows multiple transitions and fostering the non-deterministic states. This grants NFAs higher expressive power, enabling them to recognize the languages that DFAs cannot. Although NFAs offer greater flexibility, DFAs are simple to implement and analyze. Conversion between NFA and DFA is possible, but NFAs remain in indispensable state and they can also handle complex language recognition tasks in automatic theory. So let us now discuss about the applications of NFA in compiler design. In compiler design, NFAs play a crucial role, particularly in lexical analysis. Lexical analyzers utilize NFAs to tokenize the input streams efficiently based on the regular expressions. By representing regular language secondly, NFAs aid in generating the optimized lexical analyzers and facilitate them for faster compilation process. Moreover, NFAs form the foundation of constructing parsers and code generators in subsequent phase of the compiler design. Their versatility and expressive power make NFAs indispensable in developing robust and effect in the compiler system in an efficient way. NFAs also have a lot of practical implementations. For example, despite of the theoretical complexity, NFAs find practical implementation in various computational tasks. Software libraries and frameworks provide tools for construction and simulation of NFAs efficiently. NFAs are widely used in text processing applications such as search algorithms, text editors, and parsing tools. Regular explanation engines often employ NFAs to match patterns efficiently with large text. Understanding the practical implementation of NFAs empowers the software engineers to leverage their capabilities in solving the real world computational problems in an effective manner. So, in conclusion, non-deterministic finite automata serve as a powerful computational models with flexible transition mechanisms. They offer expressive capabilities beyond deterministic finite automata. Their non-deterministic nature allows for multiple transitions from a single state and enhance the language recognition capabilities. Understanding NFAs is essential for various domains, including automata theory, compiler design, and pattern matching algorithms. By exploring NFA structure, operations, and practical applications, we gain insights into their significance in theoretical and computational search and also in the real world software development. And we can also understand their indispensable role in advancing the computational parameters in automata theory and compiler designs. So at the last, I hope that you have learned a lot about non-deterministic finite automata, and we have also learned about differentiation between NFAs and DFAs and how NFAs are better than DFAs in various ways, and we have also learned about the practical implementations of it. So I hope that you have found this video helpful. So at last, I would like to thank each one of you for watching this video.